See.
Yeah, let's wait a couple of minutes.
Sure.
Did great people ever get stopped by these cops? No. Live your best life.
That means great will be it.
Yeah. I just great. Must be true.
This great.
No, okay, close enough. Order one difference.
Alright, welcome back. So time to start the afternoon session. And the first lecture will be by Raman on BSM and Naturalness. And a reminder, if you're interested, this evening there is also a public lecture by Raman at 7:30 p.m.
Great. I think my mic is on. So, very liquid chalk. What happened to the regular? Is everything? Okay. It writes. Okay. So I did one thing. I updated the references a little bit. I have to keep doing it, but I updated the references on the Google Drive, and the numbering has changed a little bit to the kind that I was referring to whenever I did give you a reference. I gave you a reference number, so that numbering is correct with the updated references. So as somebody pointed out last time, I skipped over one of the spins. I did that deliberately. And that's the case of spin 3/2. And again, if your mass is non-zero, then you would say, I know how to think about such a thing. To get spin 3/2, I should take spin 1, which I know all about, and spin 1/2. And I'm going to use the beginning of the Greek alphabet for spinor indices. How far in the beginning? I think I only need alpha and beta, so that's it, okay? So I need a vector index, I equals 1, 2, 3, so spin 1 and a spin 1/2. And from spin 1 cross spin 1/2, I can make spin 3/2. But just like when we did the tensor for the graviton, there are other possibilities that I don't want to talk about with spin 3/2. Like when spin 1 cross spin 1/2, I can also get spin 1/2. And I want to set that to 0. Okay, I need. How do you contract indices to sort of get the spin 1/2 portion of it? Well, you're not surprised if it's this, right? That this index knocks this I out, and the beta contracts. And these are Pauli matrices, and you're left with a pure spinner, spin half thing. But I need that to be 0. Okay, so that just should be one of the equations of motion should just tell me that. And similarly, if the whole game, when I relativize it, is to make everything a relativistic spinner and a relativistic vector, if that's the field, then I would need everything with the mu equals 0 index to be 0. Okay, and then what's left would be truly the spin 3/2. And so you can ask, is there a kind of a wave equation, some generalization of the Dirac equation, which gives this in its rest frame, okay, in the sort of the p equals 0 frame, turns into this. And indeed, again, there's just a unique answer. It's one you'd have to have a very efficient way of thinking in order to say was straightforward, but there is a way of thinking in which it's straightforward. I'll just write it down. Okay. So I've written it as where the spin indices are implicit. So for example, I haven't written, everything is written in matrix language, as we often do with the Dirac equation, right? I'm not writing the fact that there's an alpha index here and that something like a gamma matrix is a matrix in alpha beta. Obviously it is. So just the usual way of reading this is all you need. And this is the famous, you know, up to some factor of I or something. It's just the usual generators of the Lorentz transformation in spinor basis. Okay, so you would never guess that this is the thing that gives this uniquely in rest frame, but it is. And if you want I found it to be a slightly painful exercise, but if you want a slightly painful exercise, it's too easy being a TASI, then you could try to just show that, okay? And this is the famous Rarita-Schringer equation, and I don't think I overlapped in life with Schringer, but I'm pleased to say that I was a postdoc when at least a retired Rarita was still alive. So that's how ancient this equation is. But of course, what we care about is m goes to 0. And just like when you have fermion, I mean, the standard spin half, and you take the Dirac equation and you go m goes to 0, instead of having a 4-component Dirac equation, the Dirac equation splits into the left-handed Dirac equation and the right-handed, or the right-handed equation. Similarly, the same is going to happen here. So I can work with a 2-component spinner in case you are keeping track. Yep.
Could you remind me what our goal is here, please?
Yeah, so I've been going through all of the different spins, saying what are the relativistic wave equations, and what are the conserved charges, which are symmetries, that are required to protect the massless limit. So we're trying to say, well, what is required here, okay? Is massless spin 3/2 allowed? Remember, massive spin 5/2 is not allowed, right? As I said. I think there was a question up there. Sorry, is there a higher dimensional generalization? Yeah, there is. Yeah. I'm not sure. I'd have to think. But
There's a triple gamma matrix that's anti-symmetric instead of using
gotcha.
that works in any dimension.
Got it. Okay, so we do have some actual experts here. So the massless limit, it's just this, right? So the gamma 5, again, in a 2-component language, the gamma 5 is plus or minus 1, throw that away. But the gamma matrices instead are really just the so-called sigma matrices, where they are either the identity matrix in the 0th component or the usual Pauli matrices. Okay, so that's hopefully familiar to you. And then d rho and then psi of nu equals. And now I'm going to include a source. I'm just doing 2 steps. I'm including a source as well. As I did last time, let me call it curly j. And again, it has to sort of have the matching indices. So it's got a mu index here. And if you're keeping track of the alpha, if I explicitly put it in, there's the alpha beta, okay? Beta, right? So it also has a dangling alpha index. So it's got the same indices as psi itself. And again, you can see two things that follow. And was there a question? Yeah.
Maybe I'm missing something, but there seems to be a triple contraction of the mu's above. Is that half up or half?
Yes, this is not right. Hang on. It should.
The spinner just needs a kappa or something.
Yes, you're right. Sorry, the spinner needs a kappa. And here, same thing, right? The spinner needs a kappa. Sorry. There, kappa. Okay. Well, one thing you can see about this equation, again, is that it has a gauge symmetry, which is psi kappa beta goes to psi kappa beta plus d kappa, and some random function, which is a spinner. Okay, so a gauge transformation, which is c. Again, because if you have an extra derivative of c sitting here, then the two derivatives are anti-symmetrized, which is 0. Okay, so it does have this interesting and weird gauge symmetry where the gauge parameter is itself a spinner. And again, if I were to take d mu of this, if I take d mu of this entire equation, of this entire thing, then again, the two derivatives are anti-symmetrized, so that's 0. The left-hand side is again trivially 0. So that implies that that this current with an alpha index is conserved, and that means that there is got to be a spinner conserved charge which is the integral of this local density, where the J is made out of fields in a nonlinear way, right? The usual. Okay, so now, the question of why are we doing it? Well, this is a startling thing. Every time we've looked at a different type of spin, in the higher spins, we're finding that there's sort of a gauge theory involving conserved quantities. And here, this conserved quantity has a spinner index, so that's really weird. And the conjugate, so I'm just using bar to be the conjugate of anything. Okay, so similarly, there's the conjugate thing. Okay, so I'll try to consistently just use bar to mean conjugate. And I'm not going to try and, these are meant to be two-component spinners, and I'm not going to be, it will not be needed that I should be careful for those of you who know about dotted indices and undotted indices. Well, you can put it in, but now it's useful. I think everybody's supposed to know about two-component spinners because the standard model is chiral and it's important, but just to give you the main things that I'm using, there is this handy appendix in reference 3, which is, as I said in there, it's a review of two-component spinner indices, two-component spinners and various identities. But I think I mostly just need this. So just like SU2 is sort of roughly isomorphic to the rotation group, and that's the basis of non-relativistic spinners, SL2C, 2x2 complex matrices with unit determinant, is roughly equal, at the algebra level at least, to the Lorentz group, and that's the basis on which we get spinners, and in particular two-component spinners on which 2x2 matrices act. So in particular, the left-handed spinners, which is the one I'm going to use, transform like lambda psi left in matrix language, where this is where this comes out of here, right? So that's it. And if you happen to have right-handed spinners, if somebody gives you that in some language, we know that we can always trade them for left-handed spinners by charge conjugation. So that is secretly left-handed. And you may remember that this is just the charge conjugation is just taking so here I'll use a star just to be explicit, that you have to take the conjugate of psi right and up to some fiddling of the indices, that is a left-handed spinner, okay? That transforms like a left-handed spinner. So that's the standard stuff you mostly know. Of course, the Lorentz invariants in two-component language are, well, the kind of bilinears you form, one is Lorentz invariant, is, say, two spinners. They may be the same or they may be different. When you write that, what you're really writing is psi left, alpha, chi left, beta, epsilon, alpha, beta, the usual anti-symmetrizing epsilon. And that one can check, given this definition, is a Lorentz invariant. And we often just write this as the raised chi, or the beta being raised, raised alpha. Okay, that we raise these spinners with respect to epsilon rather than the Minkowski metric or anything like that. And then the other thing that's useful to know is the other kind of different bilinears. The other bilinear that we mostly need is if you have something where it's a psi bar chi, but both of these are left-handed. Again, now that I've told you this, everything in sight is left-handed spinners from now on. So here are two left-handed spinners, with this, but this is the conjugate of one in this way. And if we contract these, we can make a Lorentz vector, okay? So this is a 4 vector. It transforms like a 4 vector. To check which, you need to know that psi bar, not surprisingly, in matrix language, it would transform like this. Okay, so this, knowing that psi in components, this is just the conjugate of psi alpha, then in matrix language, this follows just from this, okay? Good, so hopefully this is all old hat, but since it'll get used enough, let's okay. Now, here is the mind-blowing thing. Okay, that's all boring. But here's just something mind-blowing that you get seemingly for free, just walking down this inevitability of the structure of massless spin 3 halves, is that because Q alpha is basically the integral, so Q alpha is the integral of J. What's J made out of? It's made out of fields in some nonlinear way. What are the fields? They're either bosons or fermions. So, in particular, all I'm asking you to notice is that there's some Fermi fields, and there have to be an odd number of them, okay? Because there's a net spinor index, and there's a spin statistics theorem. So the only way you could have a net half integer index is by having the Fermi fields, whatever they are, they have to be an odd number. And then you could have some boson fields to any number, right? So it must have this structure just by the spin statistics theorem. Okay. But that means that if you take a product of two of these Qs, so in particular, I'm going to start by the most interesting one, the anti-commutator of a Q and a Q bar, okay? Now, I've chosen, at first it seems like I've just taken the product, that's all that's relevant for what I'm about to say, but it's actually the anti-commutator. What am I saying? The product of, if this is conserved, and this is conserved, then the product of two conserved quantities is conserved. Because conserved means you commute with a Hamiltonian, right? So I could have just said the product of these two is conserved. But it's not good enough in real life to have conserved quantities. They're not useful if the way they're conserved requires me to look on the moon to sort of look at what's there and then try and work out what's here, and then I have to form some. It's crucial that a conserved quantity that's useful should be the integral of a local density. In other words, the sum of local contributions to the charge. So this thing is a conserved charge. It is the integral of local contributions to the charge density. That's what makes it useful, okay? I want to take Q and Q bar and create something new, which is also conserved, but also as useful, which is the integral of something, okay? Local density. Let me write this down and then you can, okay? So I claim that that if you take the anti-commutator, that it will have this structure. And the quick reason, but I'm leaving it as an exercise to you if you want to do it, to check, is that when we do this anti-commutator, we have to remember that the Fermi fields anti-commute. They have canonical anti-commutation relations, and these have canonical commutation relations. So when you do this grand anti-commutation, products like this, you'll find that in net, what happens when you take these canonical commutation or anti-commutation relations? You get two fields, commute or anti-commute, equals delta function, right? And say in space, okay? Delta function. That's what allows this to be true, that as I take, the threat is this. This is the integral dx of something. This is the integral dx prime of something. So the product will involve things at x and things at x prime. That doesn't look like just something at x, but it will turn out to be all at x because we're taking anti-commutators where, given this structure, there will be some delta function of x minus x prime somewhere. You check. Question.
By local here, do you mean within causal contact, or is it kind of less?
No, I'm saying something even simpler, which is that the fields have arguments at x or infinitesimally in the sense of derivatives of x. Okay, and then integrated. Yes, question.
These conserved charges form some sort of algebra structure. Can I play this game infinitely often?
We need to check whether the algebra, this thing, you might say too much symmetry may be a bad thing because it might just say that the world doesn't look like that, and so we want to check that there is a possible closure. So let's come to it. We first have to figure out who is this new guy, okay? And here you see, look, it involves products of a barred quantity with an unbarred quantity, and we sort of have the trick here. We have the basic insight here, but what we can write it equivalently by saying that this useful conserved quantity must be a 4-vector in disguise. Okay. It must be a 4-vector in disguise. Okay. And the 4-vector, I'm just calling it P. Now, immediately, you know why I'm calling it P. So, by the way, the convention for the normalization of these Q's, I can multiply by 2 or divide by 2 or whatever, is that the proportionality constant is 2. And who is this P? Well, it's obvious. It's a conserved 4-vector. There's only one of those in sight. It's called momentum, okay, because of this exercise, which I haven't yet uploaded, but which you'll do. Good. Whoa. So we've just figured this much out, right? Similarly, so I won't do this because they're more boring, but they're critical. If you look at the anti-commutators with barred by themselves and unbarred by themselves, these the fact that they're anti-commutators means that you can't use this rule quite. It's actually, they are tensors. They have to be Lorentz tensors. And they have to be conserved Lorentz tensors. But there are no conserved Lorentz tensors. You might say, what about angular momentum? The angular momentum tensor does not commute with the Hamiltonian, right? Because the Hamiltonian is part of a 4-vector. It's not an invariant. When you commute with J mu nu, that's like doing a Lorentz transformation, and H is not invariant. So there is no candidate in an interacting theory. There is no candidate tensor that could be these guys in disguise, right? And therefore, these have to be 0. Okay. Now, the statement is this algebra, so you can play with it. This algebra, when I combine it with the obvious, which is the Poincare algebra, which remember involves P and J mu nu, the usual one, and one sec. And again, I won't write this out, the obvious statement. When I write Q alpha, I mean it transforms like a spinner, which you can write in terms of commutators with J or whatever, and you can make it official. But you already know how things transform if they're spinners. I don't need to write it out. So if I put all of this together, then this is a spinner, okay? This is a closed algebra, okay? And it has a name, right? That's supersymmetry, which you all know, Susie. And it's really minimal. The fact that there's only one Q that I'm considering is minimal, or n equals 1 Susie, okay? Now there was a question.
Why can't they just make that proportional to epsilon?
I think because of this commutator, remember this is the anti-commutator. It sounds counterintuitive, but anti-commutator means it's Q alpha, Q beta plus Q beta, Q alpha. Yeah. Right. Yeah.
In terms of the physics that we're describing, what does it mean that the algebra is closed?
It means that if I take commutation of sort of integer spin conserved quantities, or any sort of commutators of anything that involves the integer spins, or anti-commutators involving the half integer spins, that I never get a new, I'm not able to then say that there's a new conserved quantity that has to be included in the list. Okay? So it's just the generalization in group theory of saying that here's a bunch of different transformations that all possible products, or if you want in the algebra, whatever, commutations, stay within the algebra, right? That's the usual thing. How did I get this part? Yeah, so it's very, very simple. This is easy for you to check. This is these matrices, I've written them out explicitly, identity, Pauli matrices, are a complete basis for Hermitian 2x2 matrices. Okay? They are a complete basis for Hermitian 2x2 matrices. That means, and the other thing you can check, this is, remember, this is the conjugate of this. This is Hermitian. So if this is a complete basis, and this is just a Hermitian matrix, then I can expand it with some linear superposition. And again, all the things that intuitively the notation suggests are true. The fact that it has this dangling mu index means that this quantity is a vector, right? So that it hooks up to form an invariant. Yeah.
Why couldn't we replace P mu with like the Pauli-Libansky vector?
Yeah, I have to remember which one that is. That's the
Like the
yeah,
W mu.
yeah. But it has to be so. Let me try and write it out after class. Yeah, let me do that after class. Very good. So we can ask, what does this algebra imply? And very quickly, before we do anything terribly technical, we see what it's that if this theory, if this algebra is actually consistent, like if we can actually find field theory versions of this with an interaction, that we will have a very magical structure. And it's actually needed, that there must be things like this if spin 3 halves should match all the other spin 2 and less guys and have interacting variants, okay? So the first thing is that it implies that there is such a thing as superpartners, that particles have to partner up under the symmetry. The easiest way to see it is, well, as I said, the Hamiltonian commutes with these guys. So that means that if I take the Hamiltonian Q alpha acting on, say, some bosonic particle, okay, then by this is the same as Q alpha Hamiltonian acting on the same bosonic particle. Now this is necessarily some fermion by the spin statistics connection, right? Okay, it's got half-odd integer. And this, well, if the original boson was an eigenstate of energy, then this is just the energy of that boson times the boson. Okay. And this, h of this, is just the energy of the fermion times the fermion state. But this is just a C number, right? So it doesn't matter whether I put it on this side or I put it over here. Okay, so move it over here. And then I have Q alpha acting on the boson again. And so that is just E boson acting on that same fermion. Okay, and these are equal. And so I can just erase this state. It's the same state on both sides. And it says that this boson and fermion that were created by the Q alpha, turns one into the other, are degenerate, right? So say the boson was in its rest frame or something, it basically says their masses are equal. Okay, that's the famous statement. Okay, so they are superpartners. That means all the particles have to pair up. Okay, all the elementary particles have to pair up into these superpartner pairs. Yeah. So the one case where this wouldn't work would be, suppose I did this acting on this state, say, and let's say I got 0. Okay. Now that will get us into spontaneous SUSY breaking. So let me say for the moment, let's go easy on ourselves and not worry about such loopholes. And then this is the basics. Okay. So now we can do some simple deduction in terms of what better happen if this is not inconsistent with field theory, then if it's possible to get away with this very tight extension of space. So notice it's an extension of space-time symmetry. Then if it's possible to do it, certain things will have to follow. Yeah.
Do these superpartner pairs also result from the fact that we got spin 3/2 by crossing spin 1 and spin 1/2?
So this is my shortcut to say, you might say, oh, I wanted to get it by crossing spin 5/2 with spin 4. And so you might say, is this invariant under all such choices? And the result is. And there's maybe a more, like if Nima, he would do some amplitude version of this where everything is on shell. No. But it would take longer for him to explain. So yes, this is really not, this is theorist independent. But I have made it quick for you by being this theorist, right? Okay, so we can ask, here's a famous boson, massless spin 2, graviton. And it better be degenerate with somebody. Now, it's massless. So whoever it's degenerate with is going to be a fermion with, now, since you get to it by acting with a Q alpha, I could raise its spin by 1/2 or make it go down by 1/2. But if I made it go up by 1/2, it would be 5/2 and massless. But we know that's not possible. So the only thing it could be is massless spin 3/2. Okay? Which is actually the thing we were just talking about. Okay? So in fact, because it's a superpartner of the graviton, we call it the gravitino. Okay, and now let's look at another famous boson, gauge boson. A mu. Okay, may have different species. And over here, now, if Q raises this by spin 1/2, it'll make it again spin 3/2. And maybe that's an interesting thing to study, but it would be a non-minimal SUSY because it would involve more than one spin 3/2. Okay, so it's got the minimal thing is minimal SUSY is it's got to be some spin half guy, which therefore is called a gaugino. And there's as many of them as there are gauge bosons, so it's got this gauge index, but there's the alpha spin half index. Okay. Now, what about spin half? So there's spin half. But what about some spin half which is not a gaugino? Like the electron or something like that. And remember, everything here is left-handed. Won't keep repeating that. And so if by acting on this with the Q alpha, I go up half a notch, then I end up with something that has to be a gauge boson. Okay? But I already discussed that case, and I said it's not a gaugino. So it's got to go down to spin 0. Okay, so sometimes collectively we call these sfermions. Okay, but let's name the guys that we would care about. For example, in the standard model, so we generically call these psi, and they would be left-handed quarks or left-handed leptons. There would be charge conjugate of right-handed up quark, charge conjugate of right-handed down quark, and charge conjugate of the right-handed electron. And who are these fermions? Well, we could sort of collectively call them phi for scalar, but we talk about the superpartner of all of these things by putting a tilde on everything, and that means it's actually scalars. But keep the C. Okay. Now, in some sense, you could say we finished, but there's another spin 0 guy that we pull out of all of the spin half, spin 0 partners because of its fact that we've actually seen it experimentally. Yep.
I appreciate that we're doing everything 0 because like all the fun masses have masses. But if you turn the masses back on, don't you have the option to go back up to spin 1 now and not be degenerate with your gaugino case?
If I go to mass. So which one would you want to go up in?
So all of our Fermat content. So instead of going down to spin 0, could we now go up to spin 1?
Oh, right. Yes. So if I have spin half and it's massive, I could go up to, a massive spin 1. You see, you have to do the detective work all the way. Absolutely. However, if I say that, yes, it's massive, but it is a small mass, right, which is the way I'm thinking of anything that the puny little LHC can ever find. It's just some small mass thing. So when it's a small mass, I'm a Planckian guy. But when it's small mass, you have to say, that means that this gauge boson was also, the spin 1 was small mass. And the only way we know to do that, actually, the only way it can be done in weak coupling is Higgs mechanism. So in Higgs mechanism language, we basically first have to, the fields, we identify them all pre-Higgsing, where everything is massless. And then we sort of are back to this language. So there's some part which is semantic, some part which is just the fact that the Higgs mechanism is the only way to give small mass for spin 1. Yeah.
I have a question regarding that. So when I look at the anti-commutation of my scalar generator,
Yes.
kind of tells me that if I apply Q bar twice on a boson, it actually is equivalent to a translation. I mean, looking back at the anti-commutation relation, that being equal to P mu. So
Yes.
So if I apply Q bar on a boson, that's effectively just a boson.
Yes.
And that should be equivalent to translating a boson.
Yes.
The commutation is equal to P.
Yeah.
How do I see
And in some sense,
exactly?
how do you see it?
How do I see this operation of doing spinor generator twice on a boson and that being just a translation of a boson.
I'm going to show you. I haven't shown you. I mean, you're asking how can I say it explicitly. What I'm first showing you is by deduction, it must be so, or it'll turn out that the theory is trivial in some way, right? But you're asking, can it be non-trivial? Could you please show me exactly how to? Yeah, and I'm going to show you, okay? So there's the spin zero Higgs and of course, which is h of x, and the special, so it's really a special case of this partnership, but just give it a name, the spin half Higgsino, often written with a tilde, I mean, just like everything else here. The tilde is not whether it's a boson or a fermion. The tilde is whether experimentalists have seen it already or they haven't, right? So that's why I bother to even say that. And of course it has this alpha index, okay? So one thing that you can see right off in this thing is the algebra of the charges that are associated with this gauging from this equation. It's non-abelian, right? It's not that like it's nonlinear, the p there and there's two q's here. It's non-abelian in structure, which means that this thing is somehow forming a non-abelian. Now I use that term loosely because it involves commutators and anti-commutators, but it's a nonlinear theory. It's a nonlinear theory in which you are gauging gauge theory of translations and supersymmetry, right? And like all non-abelian theories that are intertwined with such a simple algebra, the gauge coupling is just one. It's like SU2 or something with W's and photons. 1 second. So the sort of the alpha gravity is this famous G Newton. Okay, for both, that's the coupling, and just to give it the name, what do we call this incredible gauge theory, which used to be called general relativity, but now has been extended in this way? We call it either local supersymmetry. That's from thinking of these as the things that we're gauging. It's really a gauge theory of these symmetries. But it's also called, instead of calling it gravity, we can call it supergravity or sugra for short. And am I ready to come to the question? Yes, the question.
So we kind of follow this pattern of wanting to be minimal and not having these degenerate superpartners. Then when you get to the Higgs, you just go back into this spin 1/2. So is that just inevitable? Or?
Yeah, well, it is in the sense that spin zero, again, with a Q acting on it, yeah, it would have to do that. I don't really want to say that this is a different, every line here has been qualitatively different. Spin 2, spin 1. No. These two lines have actually been the same. It's just that experimentally, we've seen this guy. Otherwise, suppose we'd just seen this and not the Higgs. Then I would have just listed it along with all the other standard model fermions, and we would have just, okay, so, yeah. So speak up a little bit, partly because I'm aging and going deaf.
What was wrong for a supermultiplet with spin 3/2 and spin 1?
So it would imply that there would be it would not be part of minimal SUSY. That would be so unlike the case of the graviton where there has to be a unique graviton, you are allowed to have more than one spin 3/2 particles. And just for brevity, and because it's mostly the realistic real world case, the kind that could be the real world, I'm restricting to minimal SUSY, which is to say a single massless or light spin 3/2 particle. Okay, but so in principle, nothing is wrong. But if you track through all the consequences of it, it becomes too beautiful for the real world. But there are people that play with such theories.
Same for spin half and spin one.
Yeah. Yeah.
Is there something like technical naturalness going on here if we get this supersymmetry when the mass of this field goes to 0?
So what we're seeing is it's not even natural. As the question was about naturalness, and it's not. It's like supernaturalness in a sense because, but just in the ordinary sense that, like in this case, this degeneracy is because they are gauge fields, so that's why they're massless. Okay. The same is true here, at least if the gauge symmetry has not been Higgsed. They're also massless. Here, it didn't really matter that it was M. So if you want, let me just say it like that. The mass could be non-zero here, but it's just got to be degenerate. Okay? And similarly here. Now, when you talk about naturalness, maybe that was actually my next point. Here is a huge punchline in these two lines. Again, other than the names, the specific names, these are really the same case of spin 0 and spin 1, which is we already said that spin half particles can naturally be massless or they could naturally be very light, because they have a symmetry that is protecting them. But now supersymmetry is relating the mass to the mass of spin 0, which means that now the spin 0 guy, because of supersymmetry, has a reason why it is locked into being the same mass as the spin half, which is naturally light. Okay? So a quick summary would be to say that interacting, if we can do this, if this theory can be actually constructed, that interacting spin 0, when I say interacting, I mean not like an axion, which is interacting. It's just the lighter it is, the less interacting it is, in a power law way, right? Derivative interactions. That makes it incredibly hard to discover, which is why we haven't discovered one, possibly. Whereas if we're talking about, no, I want things which interact with order 1 couplings, just like my electron interacts with order 1 couplings, then we have been struggling so far to find the principle that would do that, whereas this does it, right? It says that if you can construct this theory, if you can write it out, then you're going to find the story of interacting spin 0, which is naturally, basically it's borrowing the chiral symmetry of its fermionic partner to say that it's naturally light. Okay, so that's where we're headed. Yeah.
Is the gauge group, or the gauge groups that describe the SUSY partners of the standard model the same as the gauge groups of the standard model?
So the standard model will have gauge groups which involve these guys, right? That index. The SUSY will continue to have those gauge groups. That's an internal symmetry. It's not space-time symmetry. And that is completely factorized or commutes with this algebra. Okay? So you can write the algebra of, if you want to take the global limit or just write out the gauge charge algebra, that'll be its own algebra of charges. And then there'll be these, and both of them will commute with each other. Yeah. Yeah.
I want to ask how to understand this E fermion equal to E boson. So since many of the particles here we discuss are massless, so I guess this E fermion equal to E boson just means that if we have a momentum of a boson,
yeah,
and if we accelerate it, there will always be another supersymmetric partner being accelerated at the same time.
Yeah. So if you want, so I'm doing it in the really fast way where I just keep track of the energy, but it's really that so if I take a massless particle, then I can give it some wavelength so that it has a finite energy, and this would still be true. But basically, you can see that would say that if I give it some wavelength that's very large, then this energy will be small, and I'm saying there has to be something with small energy. But massless is what we sometimes would call gapless. That is, I can take an even larger wavelength, then this will be even smaller, and there has to be something that matches that's even smaller. Now, what kind of particle what kind of mass could it have that its energy can be made smaller and smaller and smaller and smaller? Mass must be massless, right? So I'll pause there for lack of time, but you can re-ask the question. But I'm just telling you this is enough detective work that if you think about it, you should cover the massless case. But if it's not immediately obvious, ask me afterwards. Okay. Okay. So what have I not taken advantage of here? Okay. So of course there's that little matter of realism. And I think, as I said at lunch, realism is overrated. But none of you agree with me, okay? So here it is. So we need some non-degeneracy. This degeneracy is, again, too perfect for this world. But if we are good physicists, we'll go to a supersymmetric world next time. Okay, but this non-degeneracy might be, in the big scheme of things, just a little blip. It's a tiny non-degeneracy. It can still be much smaller than M Planck. In other words, look, I'll just tell you, what do experiments tell us? So here is the top quark, here is the Higgs, etc., right? Standard model. And but look, the superpartners, as you know perfectly well, the superpartners could be here. The superpartners of the standard model. Okay, they could just be out of reach of the LHC currently, right? Maybe we'll discover them in the new test in the future. But that could easily be the case. And of course, M Planck is sitting somewhere on the roof, and so this is a tiny non-degeneracy. However, it must be there. Like, this tiny non-degeneracy better be there, otherwise this theory is ruled out. And yet, this breaking of supersymmetry, well, supersymmetry must be a gauge theory. Okay, it must be a theory whose gauge field is the gravitino, and the full non-abelian theory involves the graviton. So how can we break a gauge symmetry? Well, actually, we know the answer. That in supergravity, which is the ultimate word, right? It secretly is. When you include gravity, when you include G Newton effects, you can't have just explicit breaking of a symmetry. It's got to be a Higgs mechanism. And so in SUGRA, this SUSY breaking, that's how I will keep writing SUSY breaking, must be the result of a so-called super Higgs effect. Okay? And not surprisingly, even the gravitino also gets mass. Okay, when that happens. So, by the way, there is this, in terms of supergravity and supersymmetry, the canonical text by Wessenbagger is written as reference 4. In terms of this structure, everything below this line about gravity and G Newton level effects, everything below here is standard particle physics, and that is the supersymmetric standard model, and a canonical reference is reference 5 by Steve Martin on supersymmetry, the minimal supersymmetric standard model. Yeah.
When the gravitino acquires a mass through this SUSY breaking, is it ruled out that the gravitino could be the dark matter?
I don't think it is ruled out. I think there is still to populate it in the right way, I think that is possible. Yeah, I don't think it's my best bet, but yeah, okay. Or at least part of the dark matter. So what did I want to say here? in most of what I'm going to talk about, I use the gravitino as back door into supersymmetry. But you see, I'm just sitting here, field theory of massless particles, or the quantum mechanics of massless relativistic particles, and I go through all the cases, and boom, I'm led to supersymmetry. Every other trick that was allowed has been played by nature. So my bet is that probably this is playing out. That doesn't mean it's playing out within your collider reach, right? But if you were to ask me, do I think this is also being played out? I would say, yeah, that's just drawing a line through all the things that have happened. Every trick in the book is being played, and so I would expect this to be played. But the reason I'm telling you this part about the Sugra part is because that if I don't care, as a particle physicist for the moment, I'm not going to worry too much about G Newton level effects. G Newton is pretty tiny at the energies we occupy. So if I do this to a Higgs mechanism, what do you get when you take the gauge coupling to 0 when you look at the Higgs mechanism? You get spontaneous symmetry breaking, right? That's the trick. So you get spontaneous. It means that that as a prerequisite of arranging something like this, it must happen not explicitly, where I just explicitly say the symmetry is not exact because I don't like it. I'm just going to make it almost exact. It's got to be the result that the symmetry is, in principle, exact, but the ground state is not, and that is not symmetric. So spontaneous SUSY breaking. Okay, just like with the global limit of gauge theories, the underpinning of the Higgs mechanism is the story of spontaneous symmetry breaking. So here, when we very sensibly don't worry about G Newton level effects, the trick that we need to get in order to get spectra that look like this is spontaneous symmetry breaking. We cannot by hand just say the symmetry is broken explicitly. That makes no sense in a gauge theory. Okay, so that's the message I wanted to give. Okay. Okay, so this is all very interesting, but there is that little question. Does such a theory exist, right? Like, here are all the constraints. If they can be non-trivially satisfied, all of this is yours, right? But if it can't, then it's a waste of time, right? So before answering that question by construction and saying, here, I've constructed it, you've now got something. I've waffled a lot about philosophy, but here's something you can take home, right, technically. I just needed to waffle a little longer. I think it's worth knowing, as I'm standing here on the Planckian stage, I think it's worth knowing something about string theory, okay? And in string theory, again, there's exceptions and weird versions. Like, there are a lot of unemployed theorists, right? So everything that is morally true, there is some legal room, okay? But I don't have time for all the caveats and this and that. So I'm just going to say it in a almost correct statement without any fine print, and that is that string, as you know, string theory is a perturbative theory of quantum gravity. It takes loops of strings. It takes graviton scattering at loop level. Takes graviton scattering at loop level, with G Newton squared corrections to the leading G Newton scattering, and it turns it into, as you know, the pictures, into, instead of whirl lines of gravitons, or whirl lines of any other particles, it turns it into whirl sheets in space-time of strings. And in these whirl sheets, the world line, normally a world line is where you are in space-time as a function of the parameter of the line. But now there are two parameters, sort of the usual one that you would have had with a world line going like this, but also something telling you where you are on the sheet in the circular sense. And so you get these kind of, as you know, famously, field theories that look to set this up, you need to have field theory in a kind of two-dimensional sense, whose fields are the space-time coordinates, okay? Something you may well have heard of, okay? And as usual in field theory, various gauge symmetries, this, that, and the other to make string theory go, anomaly cancellation is a big thing. Gauge anomaly cancellation, just like in the standard model. If I were to take the right-handed electron out of the standard model, throw it away, well, of course, that would make the electron massless. You wouldn't have a direct mass for it. But to hell with data. Is there something wrong with the theory? Apparently not at first sight, but it has a gauge anomaly, and you know that, right? Similarly, in string theory, if you want anomaly cancellation, the fields here are the space-time coordinates. So you need to have the right field content. And it turns out that the right field content is you need 10 space-time, mu equals 0 to 9, okay? When all is said and done, So a quick thing is, extra dimensions seem to come out of string theory, and they historically came out of string theory when people did not consider that a cool thing, right? Like in the days where people were more conservative and didn't want extra dimensions. But now it's kind of a cool thing that it can happen. Furthermore, they'd been doing Kaluza-Klein for a long time. Yeah, so, the thing is, Kaluza-Klein, the idea of extra dimensions has been with us for a long time. Really long time. I think even Nordstrom, who I was talking about at lunch, played with a certain kind of extra dimensional theory, which is actually really cool and has come back in style in a very different guise. So that's not really my point. It's that one could, I assume I'm talking to people who are like, I've heard too many exciting stories and I live in the real world and I don't want to know that somebody has worked on exotic things. I want to know whether they are so exotic as to be unlikely. And here I'm saying, it's at least, and I don't know the answer, I'm just saying it's at least worth taking into account that string theory has seemingly got this kind of unique power that this is non-normalizable. I should have said. Sorry, I didn't really explain my point. This theory is non-normalizable. Quantum gravity at face value. This theory is sort of famously UV finite. Again, with all the fine print, UV finite. That's sort of why we would call it, in its most basic sense, a theory of quantum gravity, that the quantum corrections are UV finite. But it seems like, as a theory of quantum gravity, and perhaps the theory, perturbatively, of quantum gravity with this kind of property, it seems to predict extra dimensions, okay, as a kind of anomaly cancellation issue. And that's at least a different way of saying, is it plausible? You could have just said, it's interesting to study extra dimensions, and I take that view. But it's kind of cool that in some way it's like seems to be forced on you when you go down thinking about a kind of finite theory of quantum gravity. And it also, I know there's a question out there somewhere, but let me also say that in order to incorporate fermions, like the real world demands, and in a very non-trivial way, to have vacuum stability, meaning there should not be any tachyonic excitations, that this seems to, again, best as I can understand, seems to force you to supersymmetry. okay? That these two things that are quite exotic, well, they may be slightly more plausible to you when you take into account that string theory has this power to sort of make finite the non-normalizable. And maybe, as far as weak coupling is concerned, at least, which is at least the lamppost of our intellects, maybe that's the only way it can be done. And then it seems to force you to these exotic ingredients. What I want you to do, I'm not trying to force you to take string theory seriously or not. I just think it's impossible to go around having opinions about string theory, which one hears in conversations all the time, without knowing something about it. And yet it's such a technical subject. So I have suggested my reference 7, which I have called a short hymn to string theory, like George I's book is a poem to the Standard Model. And this is the chapter 1 of the famous book Superstring Theory by Green, Schwartz, and Witten. And I'm just saying chapter 1, which is very introductory. It does actually have some equations in it, but it has some history, and it has perspective. And to me, that book is very poetically written, but boy, I mean, it certainly gets technical fast. But chapter 1 is readable. It does have equations, but it's readable. And I feel that one should read it. If you're never going to work on string theory ever, I feel you should read chapter 1. Okay. Yeah.
So I know almost nothing about string theory, but is the way to think about the fields being the space-time coordinates as like now our fields are sort of deformations in this multidimensional space-time?
Yeah, so there's something I said fast, which was meant to be more intuitive by the drawing, which is that this way of thinking of drawing world lines in order to create Feynman diagrams is what's called first quantized field theory. That's not what you normally learn in a field theory course. So to fully explain this any better than this, which I don't want to do, would require first sort of thinking about standard field theory in terms of first quantized language, and then seeing that this is the natural generalization. Once you then see that you're sort of led to two-dimensional field theory as a technical underpinning of string theory, then you're not surprised that it has anomaly cancellation requirements, which in this case is the number of fields. But the fields here are the coordinates of an experimentalist. So I say that fast, not to make it fully understood, but when you read chapter 1, you'll know what I'm saying. Okay, good. The second digression, because it sets us up for how I shouldn't have erased this. How are we going to construct? It is no mean feat. It is an act of, I don't know, mind-boggling genius to write an interacting theory like this. It becomes child's play once you have the trick, but it's a mind-boggling act of genius to create the trick that makes it child's play. So to warm up to that, I want to talk about the extra dimensions. Extra dimensions are like, I don't know, they're like the easier sibling, and supersymmetry is like the more tortured sibling, okay? Technically. But then maybe the tortured one is the genius. I don't know, in the family. Study your own families. Okay. So I don't even want to write this. I just want to say it. Higher dimensions involve higher symmetries. They also, higher symmetries, obviously. 4D, here's the coordinate x mu. And now we're imagining going to 5D, say, where the coordinate is extended by x mu, which I'll write as little x, and x5. So if I write little x with no index, it still means x mu. x5, I'll write it explicitly. Great. So the usual Poincare symmetry, x goes to lambda x plus a, where this is a Lorentz transformation. The usual Poincare symmetry is now going to an extended symmetry, where x goes to lambda x plus a, where this is now an element of SO 4, 1, right? Fifth dimension is the fourth dimension of space. It's a bigger symmetry. It contains, this symmetry contains this and more, just like this symmetry contained Poincare invariance and more. Okay, so that's, yeah.
And we're just assuming we added one real dimension here?
Yes, only one real dimension, yeah.
And what is that capital A?
It's this, written as a column.
So it's just a linear shift in 5 dimensions in all 5?
Well, it's the collection of coordinates. But this capital X is the position in 5 dimensions. Mm-hmm. And then this is a Lorentz transformation of that position, right? Okay, so simple things, scalar. So the simplest field in 4 dimensions, 5 little x, and it satisfies an invariant equation, which is the D'Alembert, which I'll put a 4 there because we're going to higher dimensions, but D'Alembert plus m squared, and I'll put a 4 there because we're going to extra dimensions, of phi equals 0. And that's a beautiful invariant Klein-Gordon equation for the simplest field. And over here, the obvious thing, I would go to phi of capital X, and it would satisfy the 5-dimensional D'Alembert. But if I broke down the 5-dimensional D'Alembert, right, it would look like the 4-dimensional D'Alembert and d5 squared. Right? The minus is just the usual Minkowski signature, plus some 5-dimensional mass, 5x. Okay. So we already have a sense just from writing even the free equation. We could write things on the right-hand side which are nonlinear in the fields, but we already have a sense, yeah, we can generalize 4-dimensional field theory to 5 dimensions. When you do dim reg, you're practically doing that in your heads all the time. So it's no big deal, which is why I'm showing it to you. But I want to introduce another concept, which is, again, 5 dimensions is too beautiful. Like Kaluza and Klein were probably screaming about this. In fact, I think one of them did write a theory in which the extra dimension was infinite, knowing that that is experimentally not allowed.
Is the SO41 forced?
Is the SO41?
Forced.
No, you could. It's not forced any more than SO3, 1 was forced. Like we are demanding it by saying we're studying relativity,
Well,
right?
Yeah, I mean, okay, but the SO31 is forced by relativity, but if you impose relativity in 5 dimensions, is SO41 forced?
I think it is forced because it is synonymous with relativity. Like there were various ways of defining relativity, and SO3, 1 invariant theory is what we would call relativity. That's one way to say it. And in 5 dimensions, an SO4, 1 theory is what we'd call relativity, right? In a more meaningful, taste it and feel good about it way, rather than being, the dictionary, then I would say you're looking for something in which this extra dimensional coordinate can be rotated into one of the usual ones. So we at least give me a rotational symmetry between x5 and x1, okay? Only that. But if you only ask for that, you're forced to the rest, like to close the algebra or close the symmetry, that's it. So intuitively, I'm saying, could there be another dimension that is interchangeable with the x coordinate? Bizarre, could it be? And then you're led down this path. So that's more intuitively the question that would lead you to this game. Yeah?
I mean, can you have like relativity for just 3 plus 1, and the 5th dimension is,
Yeah.
kind of decoupled?
Yeah, absolutely. And you would just say that that property, whatever x5 is measuring, it's almost like some property which has nothing to do with space-time. So for example, suppose there was some notion of color that had nothing to do with wavelengths, this, that, or the other, right? And so you have, like, everybody comes in some wavelength of a spectrum, red to blue to green or whatever, which has, and I am allowed to actually change my state. Like I am blue, clearly here, and now by willing myself, I become green. Okay, so I want to keep track of that. But I also am in this place in 3 dimensions. So I use x5 as the color that I'm allowed to move in that weird space. But it has absolutely no interchangeability.
Okay, so it's boring.
So it becomes a kind of interesting continuous label, right? Very much like internal symmetries. So that's where it goes. It goes you into completely internal quantum numbers. In fact, it's actually, yeah, it even has its uses, but I won't go into it. Okay, so there's one more concept that's useful to just say we do want something realistic, and the realistic thing is we can't have the extra dimension literally being identical in every regard. We really need to hide the extra dimension, and the idea is that the extra dimension is an interval with a length L, and then the usual 3 dimensions or 3 + 1 dimensions are drawn here as planes, and so we end up with a kind of sandwich universe, and it hides very well because this is U, and okay, so if you're very big and macroscopic, then you look a bit like a quarter coin, and to your macroscopic self, that's almost as like saying you're just flat, which is to say purely 3-dimensional. But in secret, this is what it looks like. To the wavelengths that you can access, the big wavelengths, you just can't probe. You don't have access to distances smaller than capital L, and so you don't see it. However, if I blow this picture up and I'm able to go to very short distances by accessing very high energies, then in this enormous room that is the 5th dimension, in this region, I would say that the 5D Poincare symmetry is approximately true. Okay, which is to say that L is breaking Poincare symmetry. 5D Poincare symmetry is breaking L, or the way particle physicists would write it, 1 over L, the so-called Kaluza-Klein scale, is breaking the higher symmetry, 5D, down to 4D. When we break a symmetry, in this case it looks very explicit, so far it looks explicit, but this kind of breaking by a dimensionful, positive mass dimension, so by a dimensionful scale, in other words, when you're large compared to this scale, you think the symmetry is intact. Pretty good. When you're soft compared to this scale, you don't even see the symmetry, right? That is called soft breaking. Okay. Not just in the context of extra dimensions, it is always called soft breaking. Breaking of a symmetry by a dimensionful parameter where in the UV of that scale, the symmetry looks approximate, in the IR of which it looks badly broken, is called soft breaking, okay? And so this is an example of soft breaking, and I'm saying it because it's going to come up with Susie. Good. So let me make my assessment. Yes, there's something I wanted to do quickly next time, and then I will actually get you through the technical payoff, and I'll get you through a technical payoff. And then I have the last lecture. Good enough. I think I can finish something important, meaning for BSM, I'm not doing Susie because I want to teach you Susie. I'm teaching you Susie because it is an example of a comprehensive theory to which I can hold it to standards standards that I have not even told you. I've told you some of my standards in terms of my goals and ambitions, and there's other standards, very pragmatic ones to do with the success of the standard model and precision tests and all of that. But I haven't had a chance to tell you them and to even revise that the standard model already obeys those standards and we don't want to do something bad that the standard model does good. I can't show you any example until I show you at least one example, and this is what it takes. You have to climb this much to show one example, so I'm showing you the simplest example. So that's why I'm really showing you what SUSY is, although as a takeaway, I think SUSY is a very important field theory tool, both purely for theoretical physics, because many tough problems like confinement or chiral symmetry breaking, non-perturbative problems become easier with SUSY, so it's a kind of laboratory of field theory, but also because it may well, in my view, it may well be part of the experimental world, as I was saying at lunch yesterday, in your lifetime. So I honestly believe that, not that it will happen, but it has high odds that such a thing could happen, and therefore it's important that the Jedis keep passing on a little bit of Jediism or whatever the hell it is. Okay, so that's why I'm doing it, and yet next time I want to do a very simple thing with extra dimensions to show you that they have power too, because the ultimate story is something that marries the two. The ultimate thing I wanted to show you that passes the highest standards of BSM model building that I'm aware of requires both. Both of these magical ingredients are required. Okay, questions?
So what is that thing?
Yeah, so the specific model or category of models that I'm going to show you, I want to show you, if I can just make all the tough decisions tonight, is called Gaugino-mediated supersymmetry breaking. So that's the technical name. But it's got two features to it, which is it's got supersymmetry playing out in an extra-dimensional world. And in that world, in some way, you're writing the dumbest theory you can. Given that you have these exotic symmetries, you're writing what looks like, you should just look at it and say, well, okay, fine, show me how that's going to do anything. But then as I unfold it for you and say, look, this match, you might have seen the beginning part of my lecture, I was doing a certain kind of detective work where there's a certain inevitability. I just say, I just want to study all the spins, and now I've come to spin 3/2, and I start working it out, and right? Everything just unfolds. Similarly, I want to show you a model in which you say, okay, fine, you can have that if you want. That's not going to get you far. I want to unfold it to show you that it performs a bunch of different miracles. Some of them are theoretical, naturalness, blah, 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 right, to do with the hierarchy problems and how you can maintain the kind of hierarchical structure we see in nature. Two, I want to show you how it satisfies some of the deepest mechanisms that we have in the standard model. Just to give an example, the Jim mechanism is one of the most striking underpinnings of the standard model, which controls flavor-changing neutral currents. It controls how CP violation can appear in the standard model. And it does it in a very tight way. All part of standard model. You got to learn it. If you haven't, read up on it. Read George I's book. It's got lots on that.
So Raman, we're a bit over.
Oh, sorry. So let me pause and say that I want to show how that is retained in the supersymmetric theory. Yeah.
So it's a bit over, so let's have questions during the coffee break, and let's thank Raman.